Well, hello guys, and welcome back to Mr. G Physics, the channel that can help you to improve your marks in physical sciences from grade 8 to grade 12. Here's Mr. G, and this time we're going to make a video related to electrostatic. It's a very important topic because you do it from grade 8 up to grade 12. You are all the time, in all the years, you are doing something related to electrostatic. This specific question is mostly for the grade 11s and 12. However, there is a small part in the question that you need the knowledge done in grade 8. So we're going to go through the question and together we'll see how to solve this type of work. Okay, so without saying more, we're going to start, but before we do that, don't forget to subscribe for the channel so you can get all the notifications and videos I post on regular basis. This question says the magnitude of the electrostatic force between two charges, A of -3 times 10 to the -4 coulombs and B of -2 times 10 to the -4 coulombs respectively is 6 times 10 to the 3 Newton. So the magnitude of the force, and that is an important thing here. This force between the two of them is going to have a magnitude equal to 6 times 10 to the 3 Newton. This is just the magnitude. Note the following. These charges are like charges. QA is negative as well as QB. Therefore, they are going to repel each other. So the force from B on A will be pointing towards the left. This one is force from B on A, and guys, this is like action reaction, Newton's third law, and the force from A on B will be equal in magnitude to the force B on A but in opposite direction. This one is the force A on B, and those forces, both of them have a magnitude which is equal to 6 times 10 to the 3 Newton. We are just analyzing the question, getting the data for instance. Now question 1.1 says state Coulomb's law in words. Okay, so what the Coulomb's law state that the magnitude of the electrostatic force between 2 point charges is directly proportional to the product of the magnitude of the charges. Now, if you say that, you'll get 1 mark by saying the electrostatic force is directly proportional to the product of the charges. I'll recommend you to write everything, but this is the most important part. You cannot mess here. And this is the second part, that the electrostatic force is inversely proportional to the square of the distance between them. Guys, we can write this one in symbol and say that the electrostatic force is directly proportional to the product of the charges. It means if you change one of the charges, the electrostatic force will change, alright? And the electrostatic force is inversely proportional, to write it in this way, to the square of the distance between those two charges. Now note, I'm speaking about point charges, alright? I'm speaking about point charges, not objects. So this is question 1.1. Is quite simple and there is very easy to guess those 2 marks. Question 1.2, calculate the distance between the charges. Now we have to use Coulomb's law. Okay, so Coulomb's law have a formula which we are going to use to calculate the magnitude of the distance between the 2 charges. This is question 1.2, and now we're looking for the distance. What formula are we going to use? The electrostatic force is equal to K, which is a constant, multiplied by the product of the charges 1 and 2 divided by the distance squared. This formula is going to be given to you. Therefore, try and make sure you don't make mistake with that formula because it's given to you. Okay, so that is the formula. Now we are going to substitute. I like to substitute within the same formula in the same way you take it from the formulas they give you in the exams. Okay, so now we have A and B, and I'm going to substitute what I have real fast here. Okay, note that K is a constant and is 9 times 10 to the 9. I'm going to multiply by the charges, and something important. When you're using this formula, you do not substitute the signs of the charges. So this is 3 times 10 to the minus 4. Note, I didn't substitute the sign. They are negative, but I'm not going to substitute that in the formula here. Okay, so this is 3 times 10 to the minus 4, and the other charge is negative 2 times 10 to the minus 4, but the minus must not be substituted. So it's times 2 times 10 to the minus 4 divided by the distance, which is what you are looking for. Now, what I say you must substitute like this, because if you do it like this, you already get 1 mark for the formula, you get 1 mark for the left hand side, and 1 mark for the right hand side. So out of 4 marks that this question have, look here, this is 4 marks. Out of 4 marks, I already have 3 marks. I have 3 marks, guys. You shouldn't make that mistake. So now you may rearrange the formula if you want. That the distance is going to be 0,3 meters, and that should be the answer for this specific question. That will get the final mark. So that is the final mark here. So we carry on with the question. We already have 6 marks, easy peasy. By what factor does the electrostatic force changes if the distance between the charges is now double? Show now how you arrive to the answer. So we are going to get again here to the same formula, and let's see how we approach this one. This is question 1.3. I believe it's 1.3. Let me just quickly look. Yes. By what factor the electrostatic force changes? So the electrostatic force for 1.2 was, in formula, K Q1 Q2 divided by distance squared. This was the electrostatic formula. This was the formula. Alright, that is the formula. Let's say electrostatic force 1. But now, the new situation, they changed the distance. So the new one, this is electrostatic force. I was going to write the net. Electrostatic force is equal to K Q1 Q2 divided by distance, but the distance is now double. If you go back to the question, you make sure you always go back and read carefully. The distance between them is double, so it's 2 times the distance that was before, and all this must be to the power 2. Now this one is mathematics. We have to work a little bit with mathematics. This is K Q1 Q2, and when you solve this side here at the bottom, this one here at the bottom, you get that it's going to be 4 multiplied by R squared. Alright, so now we can say that this electrostatic force is equal to 1/4 of K Q1 Q2 divided by distance squared. But what we say, remember, this was the old force. We keep it. So the factor is 1/4 of the previous one. So we can say that the electrostatic force nu is equal to 1/4 of the electrostatic of A on B. I think that was the question there. Okay, so that was the question. By what factor does the electrostatic force change if the distance between them is double? So that is the answer. I hope you really understand how to solve this type of question. There is always going to be this type of question in the test, guys. Okay, the next question said sphere B is moved and make contact with the sphere A. It is then moved back to the original position. Calculate the new charge that each sphere will have after they touch. So let's represent here quickly what is happening now. Now we have, this is question 1.4.1, that the two spheres were moved together. This is A, and this is B. The two spheres come together and they make contact with each other. They touch in each other. Now, what is going to happen? During this process, electrons are going to move from one sphere to the other. The electrons are always going to move from the more negative to the more positive. You can see here that charge A is negative 3 times 10 to the minus 4, and charge B is negative 2 times 10 to the minus 4. So, charge A is more negative than charge B. This is mathematics, okay? Negative 3 is more negative than negative 2. Therefore, the electrons are going to move from A to B. From A to B, electrons are going to move. That is important to know here. Electrons move. This is great. And as a result, there will be a new charge when they separated again. So when they separate, they will have a new charge. Okay, now how do we calculate that charge? We come here, this one is conservation of charge, remember, So we come here and we say Q nu is equal to QA plus QB divided by 2, and that will give you the new charge. This one is charge conservation or conservation of charge, and it was done in grade 10. So when you substitute everything here, Q nu, we have the charge A, remember it was 3 times 10 to the minus 4, and this time we do have to substitute the sign, times 10 to the minus 4 plus minus 2 times 10 to the minus 4. In this case, we do have to substitute the sign, and this is simple mathematics. Q nu is equal to negative 2,5 times 10 to the minus 4 Coulomb. What does it mean? It means that each of the spheres will have this charge right now. So QA nu will be now negative 2,5 times 10 to the minus 4 coulombs, and the new QB is also going to be negative 2,5 times 10 to the minus 4 Coulomb. That is what is meaning by this one, and we already calculated. It's quite simple, and if you do this one, note the following: that question have 2 marks. The 2 marks here are given for this substitution here, and for the final answer. 2 marks, but it's easy 2 marks. You just have to remember what is happening here. This is conservation of charge. Let's go to question 1.4.2. Calculate the number of electrons that were transferred during this process. So now we go back to charge quantization as and also the conservation of charge here. All right, so what we are going to know here, first of all, this is question 1.4.2. okay, we need to know that charge is equal to the product of the number of electrons multiplied by the charge of the electron. So from here we can calculate the number of electrons. Okay, so this is the formula we are going to use, but they ask us to calculate the number of electrons that were transferred during the process. So how many electrons were moved from A to B? That is the question here, which is a little bit tricky, because in this case we are not just speaking about the charge, but we rather speaking about the change in charge. So this charge here is going to be the change in charge. How much the charge change from beginning to the end. That is for this question, because they're asking you number of electrons during the process. Okay, now any change is going to be final minus initial. Now to calculate the change in charge, we can either do it for charge A or we can do it for charge B. Let's do it for charge A first and then for B. Let's do it for both. So this one, change in charge A is equal to final charge A minus initial charge A. Alright, so what was the final charge? For both of them were negative 2,5 times 10 to the minus 4. And the initial was minus, I'm subtracting, minus the initial which was negative 3 times 10 to the minus 4. Okay, when you calculate this one, you will get that this one is 0,5 times 10 to the minus 4 Coulomb. This one is the change in charge A. And we can do the same for charge B. Guys, why? One is positive and the other one is negative, because one of them gave electrons away, and in the other case, the other charge accept electron, which is charge B. You can see that it got a negative charge. Okay, so now, after we do this one, we can calculate, we go back, and we are now able to calculate the number of electrons. So, the number of electrons is going to be equal to charge. We're speaking about the change in charge because they want the number of electrons that were transferred during the process. This is why we're using the change in charge divided by the charge of one electron. It can be written QE or just E. You know what? Let's write it just E. And you know I'm referring to the number or to the charge of one electron. So if we substitute here, we can use either one. We can have that minus 0,5 times 10 to the minus 4 divided by the charge of one electron, which is going to be given to you is 1,6 negative times 10 to the minus 19 coulombs. So the number of electrons that you are going to get here is going to be equal to 3,13 times 10 to the 114 electrons. So this is the number of electrons that were transferred during the process. I think this could be a little bit complicated and important. This is a grade 10 question. So if you are in grade 11, you may forget. If you are in grade 12, it's even longer time ago. So this is how we calculate the number of electrons that were transferred during the process. You can also use the change in charge A, but remember, and this is important, this final answer must always be positive. Therefore, you have to manipulate that sign. There is nothing to say about that. It's not difficult at all. Okay, now let's go to the next one. We near the end. They say write down the definition of electric field, and I want to point something out. There is a difference between electric field and electric field at a point. You can see in question 1.4.3 is electric field, and I want you to point that out. We're speaking about electric field, but in question 1.4.5 we're speaking about electric field at a point. They are different definitions. Okay, we need to know that electric field is a region in space. It's a region in space. And the electric field at a point is how strong is that electric field we're speaking in 1.4.3 at a specific point. That is what electric field at a point is. This one is a vector quantity and we represent it with letter E. That is electric field at a point. For example, and I'm going to do this one so you understand the difference between those two definitions. Okay, so let's say we have a charge. This one is for question 1.4.3. I'm going to explain both definitions because often learners confuse the two definitions. They think it's the same thing. Let's say this is a charge, could be either A or B, it does not really matter. Let's make a negative charge because we're working with negative charge. All right, now what is electric field? We can say that this is the electric field. It's all that region around that charge. So the definition that electric field is the region in space in which an electric charge will experience a force. So this electric field is all that blue region I draw there. Now, what is electric field at a point. That refers about how strong could the electric field at a specific point. If I go here, that represents the electric field at that point. So it's how strong. Okay, so that is the difference between them. Or for instance, another point here, I want to know how strong is the electric field at that point, and this one is electric field at a point. Let's say this is 1 and this is 2, for example. So this is what we refer to electric field at a point. How strong is the electric field at a specific point in the electric field? I don't know if you understand what I mean. Now, the electric field is equal to force per unit charge. Now, this charge must be a positive charge. So this charge here must be a positive charge. I'm also going to explain that one right now. Positive charge. What does it mean? That all these points I'm testing here will be like if I placed a positive charge at that specific point. So we know how strong is the electric field at that point if the charge I used to test it, it was a positive charge. That is the difference between electric field on this side and electric field at a point on this other side. This is electric field at a point. Electric field at a point. So I hope these two definitions are now clear. Now, the electric field, and we are going back to this point here, so don't get lost yet, we are at this point now. The electric field is not represented with this cloud I make there. They are represented rather with lines, because we don't draw clouds, we draw lines, and those lines are called electric field lines. It's just another way, or the way of representing the electric field. If it's a negative charge, you know that that electric field will be represented with line pointing to the center of that charge. Let's say not to the center, but pointing towards the charge if it's a negative charge. Okay, so this is how we represent electric field. We represent it with line, we do not represent it with that blue cloud there. And that will be the question 1.4.4, if I'm not mistaken, guys. Yes, draw the electric field pattern for the two charges after they touch. After they touch, the both of them are negative and equal in magnitude in terms of size. The two charges have the same size. So therefore, they will have the same number of electric field lines. They are both negative. It means they will repel each other. Now this drawing could be a little bit more tricky than actually look. These lines will be turned all the way because they are repelling. So you don't have straight lines, guys. You don't have straight lines. They are coming at 90 degrees from the surface of the sphere, and you don't have to draw too many lines. All they have that little curve because they are pushing away from each other. The same happened with the other sphere. There we go. They are turning. They're coming out at 90 degrees from the sphere. There we go. And now I am going to draw the same number of electric field lines because they have the same magnitude. Even if you draw another line here, that line attempts to turn away from the other one. Let's say in this way, for example. The same. If I draw 2 there, let me now represent 2 here. So there are 2 negative charge. This is a way of drawing. What is the direction? It is towards the charge. So the direction is now towards the charge. If the 2 charges instead were positive charges, then the drawing would be the same, but the direction will be away from the charges. Okay, so guys, this is this question, and I hope you understand it's quite simple. Okay, this is the drawing, and this one is question, okay, we say is question 1.4.4. 1.4.4. If the 2 charges, and now this one is like in case that is one positive and one negative, all the way from positive to negative, that line in between is the only straight one. All the other lines are going to have a turn in this specific way, all right? And then you don't have to represent that one all the way, but it's also turning because it's going to be towards that line. It means that one will go all the way. I just don't want to represent it fully up until it comes to this specific point. I don't like to have that one. I've seen learners having that charge, that line, the specific one straight is not straight. Okay, so that is I keep making mistake there with the direction. There we go, and so on. So guys, this is how we represent if they were unlike charges. This is how we represent if they were unlike charges. I hope you get the idea. Question 1.4.5, we explain here about the electric field at the point. Question 1.4.5, there we go. And then guys, we are almost done. This question was long. It's a very good question because you have like everything. Calculate the strength. It means strength mean magnitude of the electric field at the point. I want to point that one also out. Strength means how strong is the electric field. All right, electric field is a vector. This one is a vector, but the strength is the magnitude of that vector of the electric field at a point 20 centimeters on the right side of point from charge B. And we have to come all the way here and represent because it's not as easy as it looks. Okay, it's not as easy as it looks. We have here, this one is question 1.4.6, and it's finally the final question. We have charge A, and all this is after the touching, okay, which is a negative charge. We have charge B here, which is a negative charge, and they say that they place a specific point, which, remember, those point charges are always positive, right? They want to know how strong is the electric field at this point, which is going to be 20 centimeters on the right side. Let me see if I'm reading correct, guys. Let me go back. I did this question 20 centimeters on the right side of charge B. So yes, I was right, reading right. 20 centimeters on the right of B. Now, what is the problem here? Remember, those charges were moved back to the initial point, okay? So they will touch each other and they will move to the original position. It means the distance you calculate at the beginning is going to be the distance here. The distance is 0.3 meters. It means that from A to B, there is 0.3 meters. All right, so now what is the problem with this specific point? This point is being affected by the electric field of A as well as the electric field of B. Both charges have an influence on that specific point. So there are two vectors acting on that point. All right, there is the electric field due to charge A. I'm going to write it here. And maybe I need to move this 20 centimeter up there because I need to write a few things here. This one is E A. The strength of the electric field at that point due to charge A. Remember, it's a vector quantity. And then we also have the electric field due to charge B, also pointing in that direction. This is E B. Why did I make it bigger? Because it's closer. Okay, so now we need to calculate the net electric field at that point. And then we go all the way to the topic related to vectors. E net is equal to E A plus E B. This is vectors all the way to the beginning of grade 11. Now, when you were working with vector, you need the direction. Direction is important. Now, note the following. Look here, and you can see that the two vectors are pointing to the left. So I'm going to say left is positive, and that will give us an addition here. Now, to calculate the net electric field, now we need the electric field of A and the electric field of B, and we are going to calculate it separated. I don't like to write too much things within the same formula. So how do we calculate? Electric field for A is equal to K charge A divided by the distance squared. All right, this is the way of calculating the electric field on a not uniform field. So let's substitute and calculate. Remember, all this is happening after they touch each other. So let's substitute what we have. Remember, that one was calculated, was the new charge calculated here, negative 2,5 times 10 to the minus 4. However, in this formula, you are not going to substitute the signs. Make sure you take the note, is important. Now, the distance from A to the point, note, is from here to there. In other ways, is the 0,3 meters plus the 20 centimeters. We cannot work in centimeter, so this one is 0,3 plus 0,2. That is the distance from A to that specific point. So you can write it like that, 0,3 plus 0,2, or you can write 0,5 already. Alright, so that is how we calculate EA. So you will get that the answer here is 9 times 10 to the power 6 Newton coulombs. That is the unit for Newton per coulomb. That is the unit of electric field at a point. So now we're going to do the same for electric field at point B, or due to B, due to charge B is equal to charge constant multiplied by charge B divided by the distance squared. Now in this case is 9 times 10 to the 9 times 2,5 times 10 to the minus 4 divided, the distance is only 0,2 squared. Alright, so what we get in here? We get the answer is 5,625 times 10 to the 7 Newton per coulomb. So all we have to do is to substitute those numbers in the equation of the net electric field, which we are going to do real fast. We're going to substitute those two numbers in there. So the net electric field, let's write it here. Remember, is the addition. Both of them are positive because both of them are pointing to the left. Okay, so E net will be equal to 9 times 10 to the 6 Newton per coulomb. You don't have to substitute the unit, plus 5,625 times 10 to the 7, and that will give you an answer in net is equal to 6,515 times 10 to the 7 Newton per coulomb. The direction, remember, we did the picture here, so the direction was to the left, as you can see it there. So the direction is to the left. All right, but when we go back to the question said calculate the strength. So how strong is the electric field? Therefore, no direction needed. The final answer is the strength of the net electric field at that point is 6,515 times 10 to the 7 Newton per coulomb. Guys, this is it. I thank you for watching the video. I hope it helped. If it helped, don't forget to subscribe for the channel, to share the video, to thumb up, to write comments. I'll see you next time. Mr. G here.